So here it is asked that in a reverse biased PN junction, when the applied bias voltage is equal to the breakdown voltage, what happens? Options are option 1, current remain constant while voltage increases sharply. Option 2, voltage remains constant while current increases sharply. Option 3, current and voltage increases. And option 4, current and voltage decreases. Now, as we are speaking about reverse bias PN junction, we should be very clear with the concept of minority charge carriers. Now, we know that in an intrinsic semiconductor, that is pure semiconductor, if it is having sufficient thermal energy, if the temperature increases, if there is sufficient thermal energy, some of the valence electrons will jump into conduction band. That means valence electrons become free electrons, and these free electrons will be called as minority charge carriers. And whenever there is a free electron put into the conduction band, there is one hole left in the valence band. This will create electron hole pairs. Now, this concept of minority charge carrier is very important to understand reverse bias concept. Now, if you see the a diagram of a reverse bias, we can see here in a reverse bias or condition, we know that the voltage applied here will be such that the negative of the battery is connected to the p-type semiconductor and the positive of the battery is connected to the n-type semiconductor. Now this is going to attract the majority charge carriers back towards the battery. That means in p-type the holes are majority charge carriers. These are attracted over here because holes are positive charge particles, and even in n-type electrons are negative charge particles, they will be attracted here, and the depletion layer is increased. The depletion layer in between is increased. Now, if you remember the minority charge carriers, now minority charge carriers, that means in p-type semiconductor, electrons are minority charge carriers. So here you can show some electrons which are minority charge carriers, which are negative charge particles. Similarly, in n-type semiconductor, holes will be minority charge carriers, which will be positive charge particles. Now here, if you see this supply here, a battery supply, the negative of the battery now is going to have an impact on the electrons, which are the minority charge carriers of p-type semiconductor, and positive of the battery is having the impact on holes, which are minority charge carriers of the n-type semiconductor. Now for these minority charge carriers, this type of battery arrangement is acting like forward bias, so putting a force on it to cross the depletion region. Now initially when the voltage is increased, when the applied voltage is increased, very few minority charge carriers are able to cross the depletion region. Now here we see that if a reverse voltage is increased continuously, the kinetic energy of the minority charge carriers becomes high enough to knock out these electrons from the semiconductor atom, so that these electrons become free electrons and they come out and join the flow of current. So here at this stage, when the reverse voltage reaches the breakdown voltage, we see that there are sufficient minority charge carriers which are forming a large amount of current to flow. So here you can see a large amount of current is going to flow because of minority charge carriers at a breakdown voltage which remains constant. That means the voltage applied is remaining constant, whereas the current which is flowing is increasing. So therefore, out of these options, option number 2 will be the right answer, which says that in a reverse bias PN junction, when the applied bias voltage is equal to the breakdown voltage, the voltage remains constant while the current increases sharply.